Hello everyone. In the last class, we had talked about roster form of a set. Today we'll talk about set builder form of a set and we'll see some operations on sets. So set builder form of a set. Earlier we had defined it as in the set builder form of a set, we simply write the characteristic property of the elements of the set. Now, when I say characteristic property, I mean that property which can be used to identify every element in the set. So we'll take up some examples. Let's talk about the first here example. It is a set which has a 2 and 8, a 4, an 8, 16, and 32. All of them I observe this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3, a 2 to the power 4 here, 2 to the power 5 here. So this is the property that is being displayed by the set, which is every element in this set is actually of the form 2 power n. N is some natural number. So let me write the set builder form here. Now in the set builder form, how we write it is first we use the braces again. It would be collection of all those x such that x is of the form 2 power n. Now we had observed every element in this set is of the form 2 power n. Now I need to describe what this n is, the n that I have written here. So where this n is, so let's see what happens with the n here. The first element that I see here, which is 2, is obtained when I take n is equal to 1. The second element is obtained when I take n is equal to 2. The third element is obtained when I take n is equal to 3, and so on. That's how the counting goes here. N is a natural number. That's what I see here, where n is a natural number. So this is going to be the set builder form of this set. Similarly, we'll consider the next example. This time we have 2 here, a 4, 6, 8, 10, and so on. So what we are observing is the elements in this set are multiples of 2. So the way of writing this set would be, then again, just like we wrote in the last set, collection of all those x such that x is a multiple of 2. Now multiples of 2 are written as 2n. Now again I need to describe what this n is. So again, just like the last question, we have n is a natural number here. Now when I say n is a natural number, it means n can be anything inside this collection of natural numbers. This collection is infinite, the set is infinite. Let me take a different example. Let me take a finite set instead. So when I take a finite set here, let me take 2, 4, 6, 8, 10, 12. Unlike the last question, which was an infinite set, I have only taken first 6 multiples of 2. I've only taken first 6 multiples of 2 here, and then I need to write the set builder form then again. So just like the last one again, it is we are collecting all those x which are of the form 2 power n, 2 times n, it's a multiple of 2. Now again, now this time, unlike the last question where set of natural number was there, my n is going to be finite in number. There are only finitely many elements in here. So this n are going to be finite in number as well. So this is going to be where this n is, it is either 1. When I take n is equal to 1, I get 2 into 1, which gives me the first element. When I take n is equal to 2, I get the second element. When I take n is equal to 3, I get the third element. The last element comes when I take n is equal to 6. So this counting that I've written here only goes on for n from 1 up to 6. N is equal to 1, 2, 3, 4, 5, and 6. So let me rewrite it as n belongs to this set, the set which has first 6 natural numbers. So this is a set builder form for the set that I've taken 2, 4, 6, 8, 10, and 12. Now set builder form of a set isn't really unique. It does represent one single set, which is this one itself, but I can write the set builder form in one more way. I can write it as, instead of writing x here all the time, I can just start with the form itself. The form was 2 times n. So I'm collecting all the elements of the form 2n such that then again n would be of the form 1, 2, 3, 4, 5, 6. So there isn't really a unique way of writing a set builder form. You can write a set builder form in multiple ways. I've taken up two more examples here. One is 1, 4, 9, 16, 25, and so on. What I observe is every element in here is a square of some natural number. Here, this would be square of 1. This is a square of 2. This is a square of 3, square of 4, square of 5, and so on. So elements are of the form. So the set builder form here would be collection of all those natural number x such that the elements are of the form of a square. So which is x is of the form n square, where n is a natural number here also. When I take n is equal to 1, I get the 1 square, which is the first element. When I take n is equal to 2, that would be square of the second element. N is equal to 3 gives me the square of the third element, and so on. To write it in other way, I can simply rewrite it as, I'm collecting all the elements of the form n square such that n is simply a natural number. So it is one more way of writing the set builder form here. And lastly, I'm taking up this example: 1 by 2, 2 by 3, 3 by 4, 4 by 5, and so on. Again, it's an infinite set there is. So I want to write the set builder form here. What I observe is whenever there is some element in the numerator, in the denominator, I have one larger number, which is n plus 1. So when n is the number in numerator, the number in the denominator is n plus 1. Now I write the set builder form here. It would be collection of all those elements of the form x such that x is of the form n by n plus 1. And now I need to describe what n would be, where when I take n is equal to 1, I get 1 by 2. When I take n is equal to 2, it would be 2 by 3. When I take n is equal to 3, it would be 3 by 4. When I take n is equal to 4, it would be 4 by 5, and so on. Again, I see n is simply a natural number. N was 1, 2, 3, 4, 5, and so on. That's how the counting goes. This collection is basically the collection of natural numbers. So I can just rewrite the thing as n belongs to n. So that's the set builder form of this last set. So all we are doing when we are writing the set builder form is just trying to identify what is the defining property every element displays, and then we are simply writing the property. In the first example, it was powers of 2. In the second example, it was multiples of 2. In the third example, it was square of natural numbers. In the fourth example, we observed the property was whenever there is some number in the numerator, denominator has one larger number. So moving on, we'll talk about operations on sets now. So we are going to consider three operations for now. One is union of sets, the second one being intersection of sets, and the third one being difference of sets. Now, definition of union of sets is simple. I'll just illustrate it through an example. When you're talking about union of a set, you simply collect the elements which are there in A, which are there in B. So I'll take up this example. I'll just illustrate it using examples. I have A is equal to 1, 2, 3, 4. A is this set. B is the set where I have 2, 3, 22, 0, and 99. Third set that I've taken up is C. C has 4 in it, 5 in it, 1, 7, 11, and 5. So I'm treating this 5 as an element of the set C. So in this particular case, phi is acting as an element of the C. Phi belongs to C. Anyway, so coming back, We want to talk about union of two sets A union B. So definition of union of sets is given two sets A and B. The union of A and B is denoted by A union B here, and it is the collection of all those elements which are either coming from the set A or they are in the set B. So when I'm talking about union of A and B from here, A union B would be you collect the elements of A which are 1, 2, 3, and 4, as well as you collect the elements from B also. So I'll collect the elements of B this time. I'm not writing the 2 because 2 is written here already, so I don't repeat. 3 also I won't write because again 3 is already accounted for here. The 3 is accounted for already. So the next element in the set B is 22. So 22 here. The next element is 0. The next element is 99, and that's it. So this is what A union B is, and that's it. So in the union of sets, we are simply taking the elements of A, taking the elements of B, and then putting them together. In the intersection of two sets, we simply collect the common elements. Simply collect the common elements from A from B. So A intersection C would be collection of common elements of A and C. Now A has 1 in it, 1 is there in C also. So 1 is a common element of A and C. So 1 I'll collect. 2 is not there in C. So 2 is not a common element. We will not take it. 3 is here in A, but 3 is not here in C. So we'll not take 3 either. And then A has 4 in it. C has it too. So 4 is a common element as well. So intersection of A and C is going to be this set which has 1 and 4 in it. The third thing I've taken is A intersection B union C. So I have to take the intersection of A with B union C. Let me solve this bracket thing first. I need to collect elements from B union C. Now, when we were talking about union, we are simply collecting elements of B. We are simply collecting elements of C and then putting them together. So collection of elements from B. B has 2 in it, 3 in it, 22, 0, 99. And then elements of C are 4, 5, 1, 7, 11, 5. So these are all the elements of A, B union C here. Now the thing that I am up to, which is finding A intersection B union C. Intersection means I need to take common elements. So let's talk about the common elements then. A has 1 in it, B has 1 in it as well. So the intersection will be having 1 in it. Next, A has 2 in it, so does B union C. A has 3 in it, B union C has it too. A has 4 in it, B union C has it as well. So all the elements of A are there in B union C. So I'll just write all the elements of A here, which basically means A intersection B union C here is actually equal to A itself. So this is what union and intersection of sets mean. When we are talking about union of sets, we are collecting the elements of A, collecting the elements of B, putting them together. This this idea also extends to 3 sets, 4 sets, and so on. And as for the intersection of two sets, we are simply collecting the common elements. This common thing we write by and. This the idea of unions is usually we write it by or. So we are either taking elements of A or B. This or is inclusive, which means they may be there in both of them as well. Anyway, moving on to the idea of difference of sets. In the first two sets, union we have considered, in intersection we have considered. Now considering we'll talk about difference of sets. So given two sets A and B, the difference of A and B, which is denoted by A minus B, it is the set of all those elements which are there in A but not there in B. So we'll collect the elements of A, but they must be in A alone, not the B. So A minus B is the collection of all those X such that X belongs to A, but X does not belong to B. So let's consider it via example A minus B. A minus B means you have to collect elements of A not in B. Order matters here. A minus B would mean A minus B means you have to take elements in A. Whatever element you are taking, it should be in A, but that element, which is X we are taking, should not be there in B. This is what A minus B represents. The element X that we are taking should be there in the first set, but not there in the second. But when I talk about B minus A, I'm talking about element should be there in the first set, which is B in this case, but it should not be there in the second set, which is A. So A minus B means the element you are taking should be in A, but not in B. The B minus A means you're taking elements from B, which are not there in A. Let's consider it using an example now. A minus B I want to find, given A as same example as the last one, except we are supposed to find the differences this time. So A minus B means I have to take elements from A, but they must not be in B. So let's see what it is going to be equal to. Let's talk about this one. One is there in A, but one is not there in B. So I can take it. I'm collecting elements which are in A, but not in B. So one is there in A, but one is not in B. 2 is there in A, but 2 is there in B also. So I will not take 2. 3 is there in A, 3 is there in B, 3 will not be taken. 4 is there in A, but 4 is not there in B. So 4 will be collected. So that is what A minus B would be. We are collecting elements of A which are not in B. Second example, we are supposed to take union of A minus B and C. But then A minus B, we found it just a while back. It is 1 comma 4 and C is here. So I want to find A minus B union C. So I'll just collect the elements from A minus B. I'll collect the elements from C, put them together. So A minus B has 1 comma 4 in it. And now I'll collect the elements of C. So elements of C are 4, which is written here already, 5, 1, which is written here already, 7, 11, and the last element of C, which is 5. So this is what we have. A minus B union C is equal to 1, 4, 5, 7, 11, and 5. And lastly, we need to find A intersection B minus C. Now the B minus C would be, we are taking elements from B. The element we are taking should be in B, but it should not be in C. X belongs to B, but X does not belong to C. So let's see the element in B. The element 2, which is there in B, is not there in C. So we'll collect the 2. The element 3 of B is not there in C. So we'll collect the element 3. 22 is not there in C either. 0 is not there in C either. 99 is not there in C as well. So this is what B minus C is going to be. Now I need to find A intersection B minus C. So that would be A intersection B minus C. A is 1 comma 2 comma 3 comma 4, and then B minus C is 2, 3, 22, 0, and 99. Intersection means you have to look for common elements. There is 2 as one common element. 3 is also a common element, and that's it. So this is what A intersection B minus C would be. It is the set which has 2 in it and 3 in it. So these are the three operations we have talked about now. We have talked about operation of unions, we have talked about operation of intersections, and we have talked about differences of sets. In the operation of union, we are collecting the elements from both the sets, putting them together. In the intersection, we are looking for common elements among the sets. In the difference of sets, we are taking the element, if we are talking about A minus B, we are collecting elements from A which are not there in B. Now let's look at some properties of union of sets. Union of A with B is same as B union of B with A, which is called the commutative property. So union operation satisfies the commutative property. It satisfies the associative property as well, which is union of A with B. Then you take the union with C is going to be same as union of A with B union C. Third property, A union phi is same as A. Now phi is a set which has nothing in it. So when you're taking union of A and phi, it, it is equal to A itself. Union of A with itself is A itself. And lastly, union of universal set with the A is universal set. Now we'll talk about what this universal set means also. I'll just take it and take an example and then define it. So these are the five properties we have on operation of unions. Commutative property of union holds, associativity holds, union of A and phi is A, union of A with itself is A, union of A with universal set is the universal set itself. So let me take up the example then. I have taken a random set U as 1, 2, 3. There is this set which has these many elements and 1, 2, 3, 4, 0, 22, 99, 5, 7, 11, and 5. So these are the elements I've taken up in the set U here. Now what a universal set is, it is simply a set which is acting as a container for the sets that I'm taking. Everything that I've taken in A is coming from the set U. Everything that I've taken in B is coming from the set U. And then everything that I'm taking for C is coming from U then again. So it's in this regard that we are saying U is the universal set. Now having taken the set U and then having taken A, B, and C, every element of A is in U, every element of B is in U, and every element of C is in U. Now first we'll verify associative property of unions. Now the associative property of unions says union of A with A union B union C is same as A union B union C. So we'll simplify the left hand side, we'll simplify the right hand side, and then we'll see whether they are actually equal. So let's consider the left hand side. In the left hand side, I'm supposed to find A union B, then we take the union with C. Let's see what union of A with B is. Collect the elements from both of them. So that would be 1, 2, 3, 4, and then 22, 0, and 99. And then we'll just take the union with C now. A union B, union with C would be union of this set with the C, which is this set. So I'll just write the elements then. A union B we have just found 1, 2, 3, 4, 22, 0, and 99. And then I need to take the union of this set with C, and C has 4, 5, 1, 7, 11, and 5 in it. Now taking the union now, it would be 1, 2, 3, 4, 22, 0, 99. And then the other elements from the set C, that would be a 5, a 7, an 11, and a 5. So this is what A union B union C is. In a similar manner, we do the right hand side. So I'll skip the work this time. A union B union C is same as, so A is 1, 2, 3, 4. Union of B and C would be 2, 3, 22, 0, 99, a 4, a 5, a 1, a 7, an 11, and a 5. So when you collect the elements of both of them, it becomes 1, 2, 3, 4, and then 22, 0, 99, 4, 5, 7, 11, and a 5. We observe elements of A union B union C, which has 1, 2, 3, 4, 22, 0, 99, 5, 7, 11, and 5. Both of them are becoming same, and then it verifies our result, which is A union B union with C is actually same as A union B union C. This verifies the associative property for us. Next property we'll consider is the law of U, the last property, which says universal set. When you take the union of universal set with the set A, it is going to be equal to universal set itself. So universal set is this set for us. A is this set for us. We need to check that the right side is actually equal to U. So this set is the universal set itself. 1, 2, 3, 4, 0, 22. Yeah. Every element of this set is actually the element of universal set. So this set is basically universal set itself. So we need to take union of the universal set with the set A. So this is what our universal set is. The set A is the set which has 1, 2, 3, 4 in it. And now we are talking about union of them both. So that would be, when we are talking about union, we are taking the collection which has elements of both these sets. So we'll just collect the elements of each of these sets. 1, 2, 3, 4, 22, 0, 99, 5, 7, 11, 5. And then we need to consider elements of A also. But since everything is accounted for already, I don't have to rewrite them. So the set closes here. So this is basically the set U itself. So this verifies our result, which says union of the universal set with A is same as universal set itself. So we have verified the property of associativity. We have verified the law of U. Similar are the properties for operation of intersections as well. Just like operation of unions, we have properties for operation of intersection as well. First property, similar to what we had in unions, intersection of A with B is same as intersection of B with A, and this is called the commutative property. Intersection of A with B, then you take the intersection with C, is going to be same as A intersection B union C, and that is the associative property. Phi intersection A is same as phi. Now when we talk about taking common elements, we consider the elements which are common to both the sets, but phi has nothing in it, so there would be nothing common in them both, and that's why we have the intersection equal to phi. Similarly, intersection of universal set with A is going to be A itself, because every element of A, if you remember, every element of A comes from the universal set, which means every element of A is going to be common here as well, and that's why we have the intersection equal to A. A intersection A is obviously equal to A, and these two are some important properties called the distributive property. Distributive property says one is intersection is distributing over union, the other one is union is distributing over intersections. The property says intersection of A with B union C is same as, so this intersection distributes over these two terms here. It's like A intersection B first, union in the middle, A intersection C then. So intersection has distributed. In the second one, union distributes. So you will have A union B, intersection in the middle, and then A union C here. And then in just like in the last problem, we have to verify the property of associativity. We have to verify the law of universal set, and we have to verify the distributive property of intersection over union over intersections. So I'll just consider the third one. First two are what you do similar to what we did in the last problem. They are similar to what we did in the last problem. Associative property, which is A intersection B intersection C, is same as intersection of A with B intersection C. Law of U is intersection of universal set with A is equal to A. So let me just take up the distributive property of union over intersections. The other two are similar to the preceding example. So in the universal set, the distributive property here is A union B intersection C equal to A union B intersection A union C. So left hand side would be A union B intersection C is what we are considering. So let's find the B intersection C, which I think we already did in the last question. Okay, not there. So A union B intersection C. So A for us is 1, comma 2, comma 3, comma 4. And then we are taking the union of this thing with intersection of B and C. B intersection C comes from here. 2 is not a common element, neither 3, nor 22, nor 0, nor 99. Okay, so it's an empty set here. So B intersection C is an empty set. So A union B intersection C would be 1, 2, 3, 4 union empty set. Since empty set has nothing in it, it is simply going to be 1, 2, 3, 4. So this is what the left hand side is giving me. Union of A with B intersection C is actually equal to 1, 2, 3, and 4. For the right hand side set, we have we need to consider A union B intersection A union C. So let's find each of them individually first. Union of A with B would be 1, 2, 3, 4, and then you collect the elements from B also. That would be 22, 0, and 99. Then it would be union of A with C. That would be 1, 2, 3, 4. Then again, this time elements from C are 5, 1, 7, 11, and a 5. Now, since we are looking for common of them both, that would be A union B intersection A union C is equal to common elements are 1, 2, 3, 4, 5, 7. Nothing else is there. So this is the set then. So we observe then again the left hand side set, which was A union B intersection C, is actually equal to union of A with B intersection union of A with C. So this is the distributive property verified here. The distributive property of intersection over unions can also be verified in a similar manner. So this verifies the result we were talking about, union of distributivity of union over intersections. Now let me take up a few examples based on the operations we have talked about, and then we'll end the lecture. So I'll just take up these two examples for now. One is talking about finding union. The other one is talking about finding intersection. So let's consider the first question. In the first one we have, question says, suppose you are given a polynomial of the form ax square plus bx plus 6, and sum of roots of this polynomial is 5, product of roots of this polynomial is 6. If S is a set given by, collect all those real numbers such that f of x is equal to 0 and t is equal to plus a plus b, a minus b, then what can you say about the union of the two sets? So let's talk about the first set, In the first set, we have collection of all those real numbers for which fx equals to 0. Now fx for us is, let's consider the equation that we have. Fx is equal to 0 would mean ax square plus bx plus 6 is equal to 0. So I'm looking for those x for which this polynomial takes the value 0. But then there is some more detail given to me. It is sum of roots is 5, product of roots is 6. That is a plus b, sum of roots, which is 5, would be minus b by a is equal to 5. Sum of roots is given by minus b by a, and that is equal to 5, which tells me b is going to be equal to minus 5a. Similarly, product of roots would be c by a, c being 6 by a in this case. So the product of roots is 6 by a, and question says product of roots is 6 here. So 6 is equal to 6 by a, which when I solve for a gives me the value of a. A is going to be equal to 1, and then using the preceding equation here, b is going to be minus 5. So these are the values of a and b for me. As soon as I found the a and b, the fact that fx is equal to 0 tells me this equation that we were talking about earlier, let me call it as 1. This equation 1 becomes x square minus 5x plus 6 is equal to 0. Solving for the roots, you can use the quadratic formula to solve. You'll get the two values as 2 and 3. So the roster form of the set S becomes, in the set S, we were collecting the elements of from R which make this polynomial take the value 0. So the roots of the polynomial f, basically, the roots are 2 and 3. In the set T, we are considering taking, T takes elements of the form a, comma a plus b, comma a minus b. Now a is 1, a plus b is going to be minus 4, a minus b is going to be 6. So these are the two sets we have, S and T. Now S union T is what we want to talk about. So the union of S with T would be collecting elements from S, which are 2 and 3, collecting elements from T, which are 1, comma minus 4, comma 6. So this is what the union of the set we are talking about would be. S union T is equal to the set which has 2, 3, 1, minus 4, and 6 in it. So we were given a polynomial, sum of roots was given, product of roots was given, S was defined as roots, set of roots of F. T was this set which has a plus b, a minus b in it. We used the relation about roots of a polynomial and a relation between coefficients and roots. So sum of roots was minus b by a, which gave me this relation. Product of roots is c by a, c being 6. So product of roots is 6 by a is equal to 6. It gave me the value of a, using which I found the value of b, and then I solved for the s, I solved for the t, and then I took the union. Union of s and t was 2, 3, 1, minus 4, and 6. And lastly, I'll take up this example. Consider the polynomial fx. X squared plus ax plus b is the general form of this polynomial. Two more things are mentioned here. 0, comma 0, 1, comma 3 lie on the parabola which is defined by this polynomial. So these are 2 points which satisfy this equation. Fx is equal to x squared plus ax plus b. If S is the set of all the roots of the polynomial fx is equal to 0, they are the roots of this equation, and T is of this form, what can you say about S intersection T? So just like in the last question, I'll try to find the values of A and B if possible, and then we'll talk about S and T from there. The polynomial I have is f of x is equal to x squared plus ax plus b. let me call it a y. Question says 0 comma 0 lies on the parabola, or it satisfies this polynomial that we are known that we have been given. So x coordinate is 0 and the corresponding y coordinate is also 0. So let me put x is equal to 0 and y is equal to 0 in this equation 1. So y is 0, x is 0, 0, 0 lies on parabola. It will satisfy the equation 1. 0 comma 0 satisfies equation 1. So we'll have when x is 0, y is 0. So this thing becomes 0y, and then x square would be 0 square. A into x would be 0 plus b. That gives me the value of b. B is going to be 0. Then the second point we have been given is 1 comma 3. 1 comma 3 lies on the parabola, so it will satisfy the equation of 1. 1 comma 3 lies on parabola, so it will satisfy equation 1. Meaning in the equation 1, you can put x is equal to 1, y is equal to 3, y is equal to 3, x is equal to 1, and this is what I have. So a plus b would be equal to 3 minus 1, which is 2. But then b I have found earlier, b is 0, so a is going to be 2 here. So this is what I have. The value of b is 0, the value of a is 2. Having found a and b, the polynomial fx becomes x square plus 2x. And since I was looking for roots of this polynomial, it would be, I'm putting it equal to 0 to solve for x. That would be x into x plus 2 is equal to 0. And that would give me the two roots here. X is 0 and x is minus 2, which gives me the set S. S is going to be, S was the set of roots. Roots are 0 and minus 2. So the S is going to be 0 comma minus 2. Coming to the set T, T was f evaluated at 0, f evaluated at 1, f evaluated at minus 1. So this is the polynomial fx. I need to evaluate it at certain points. One is x is equal to 0. Then I need to evaluate it at the point 1. Then I need to evaluate it at the point minus 1. When I put x is equal to 0 here, I have 0 plus 0, which is same as 0. So the first element f0 is 0. Now I'll talk about f1. You put x is equal to 1. When I put x is equal to 1, it would be 1 plus 2. That would be 3. And lastly, I have minus 1. When I put x is equal to minus 1, this would be 1 and this would be minus 2. 1 minus 2 would be minus 1, and this is what t is going to be. Question was find the intersection of s and t. So the intersection takes common elements of the two. So the common element, I only see one common element, which is 0. So this is going to be the intersection of s and t. And that's it. So I'll stop here for the day. Have a good day, everyone.